Most structural elements in practice are exposed to loads that produce a combination of different internal stresses, such as tension, compression, shear, bending, torsion, etc. Bending stresses are commonly encountered in beams and slabs, normally in combination with shear stresses. Compression members, such as columns, usually have axial, shear, and bending stresses combined as well. But what exactly is a bending moment? This is Javier Encinas, and today we're going to discuss what exactly is a bending moment and how we use it to design flexural members. Let's get started. Bending moment is a measure of the effect produced by a load which tends to bend a structural member. The higher the bending moment at a given beam section, the higher the probability that the beam will bend at that location. For example, a simply supported beam loaded with a uniform load will be more likely to bend at the mid-span than at the supports. Therefore, the maximum bending moment occurs at the mid-span. Engineers quantify the bending moments in terms of key feet or kilonewtons meter, so it's a force distance unit. This is because a bending moment can be represented by a couple of parallel and opposite forces P acting at a distance x between them. Therefore, the moment is Px. When the curvature of the beam produces tension at the bottom, the bending moment is positive. When the curvature of the beam produces tension at the top, the bending moment is negative, as shown here. Loads, shears, and bending moments are closely related by this well-known equation. Basically, this equation indicates that the difference in moment between M2 and M1 is equal to the area of the shear diagram between the points x1 and x2. If we remove the integrals, then dm over dx equal to v. dm over dx is the derivative of the moment, and this expression indicates that the shear value at any point represents the slope of the bending moment diagram at that point. Depending on the applied loads, both the shear forces and bending moments vary along the beam to comply with the static equilibrium of forces. Formulas have been developed to calculate the shear forces, bending moments, and deflections for single span beams with different loading and support conditions. These equations are useful to quickly calculate the maximum internal forces in the beam. These are some examples, and more cases can be found in multiple publications. Note that the typical information that is provided includes formulas for shear and reactions and bending moments and deflections, also the location of the maximum moments and the maximum deflections as well. So this information is very useful for simple cases. Since the shears and bending moments vary along the beam, the best way to represent their values at any point is by the use of shear and bending moment diagrams. For continuous beams, the generation of the shear and moment diagrams may become very complex and time-consuming, particularly because the negative moments and reactions at the support locations are unknown. Many analytical and numerical methods have been developed to calculate the shear and bending moments along the continuous beam. At the end, the shear and bending moment diagrams will reflect the static equilibrium and the compatibility of the formations in the system. Some simple cases of continuous beam can be found in some publications, as shown here. But for unequal span lengths or more complex type of loads, it's necessary to develop the shear and bending moments diagrams from scratch. To illustrate how as-deep concrete calculates the shear and bending moment diagrams, I have prepared an example. This is a continuous beam of 3 spans with 1 cantilever. Basically, I specify a section in geometry, 12 by 24. Here are the 3 spans. They are unequal spans, 24, 24, and 26 feet. The cantilever is 6 feet long. Then I enter some material properties, and I enter some uniform and concentrated loads as shown graphically here. Then the program immediately calculates the shear diagram and the bending moment diagram as shown here. It can be sorted by load combination, and it varies according to the selected combination. You can see here. The program also can show all the spans or just a particular span. For example, the span number 1 look like that. span number 2, and so on, where we can see the whole beam. As you can see, it's very easy to calculate the shear and bending moment diagrams using ASDIP, both ASDIP concrete or ASDIP steel. Not only can be sorted by load combinations, but also when you change something in the input information, that change is immediately reflected in the output as well. With this, we conclude the presentation of the shear and bending moment diagrams. We can see how important these two forces are for the design of flexural members such as beams or slabs. Please subscribe to the channel if you want to receive notifications in the future for similar videos. Thank you for your attention.